Hi everyone, welcome back. I hope you had fun playing around with Conway's Game of Life there. So you're probably wondering at this stage what all this has got to do with policing, and hopefully, as we go on today, you'll start to see how some of these behaviours, these behavioural dynamics, and this way of modelling can be really useful. Um, but we started off with a really simple example. And the cellular automaton is just a simple example of an agent-based simulation. It captures those principles of individual level behaviours leading to more complex behavioural dynamics. Um, so my PhD was actually in agent-based simulation, and it was all about modelling the behaviour of foraging bumblebees. I'm trying to use a model of bumblebee foraging to try and determine whether, if we had an environment that contained both genetically modified and non-genetically modified crops, whether bumblebees, because they're significant pollinators, would cross-contaminate the non-GM crops with GM pollen. Um, and I actually used an agent-based simulation approach to do that, to model those individual level foraging behaviours. Bees have very simple energy-motivated behaviours, but then looking at the landscape scale, seeing how those individual behaviours translated into landscape scale movement. And so, if you'd like to learn more about this, you could ask me, and I'd be very happy to tell you. It was a really interesting research project. Or you could buy my book. So this is an unashamed plug. It's just £69 on Amazon, which frankly is a bargain. But do grab it quick. It's sold at least one copy in 7 years. So do grab that while stocks last. Um, you can wake up the printer perhaps by purchasing a copy, or you could just go and read it for free online, and I'll give you the link for that at the end. But you do get it in a lovely cover there. If you do want the tactile feel of reading this in your hands from a wonderful, enthusiastic academic, then do buy that. So on to today, and we're going to be showing you how to use a package called MESA. And MESA is a Python-based framework for agent-based simulation, in the same way that SymPy is a framework for developing discrete event simulations in Python. MESA does the same, but for agent-based simulation. Like SymPy, it's completely free and open source, and unlike SymPy, it has some fantastic visualization capabilities, because actually the visual aspect, as you'll already have seen in the cellular automaton example, is actually really important for agent-based simulation. So it's got some really good visualization stuff built in already, and it's really easy to use. And so we'll be showing you how to do that. And Mesa's actually really easy to use. Once you learn the basics, it's really quick and easy to put together agent-based simulations. And as I say, today we're going to be focusing on building up a disease model, so you can see the general principles of how this works. So here's today's task, and we're going to be gradually building up this model together. So you'll need to make sure you've got MESA installed, and you've got Spider, or your IDE of choice, open and ready. Do feel free to pause this video at various stages. I'm going to be showing you various blocks of code. Each time I show you a block of code, I'll first talk you through that code to explain what it's doing, and then I'll get you to write that. So at that point, just give the video a little pause, so you've got time to write in that code. Obviously, feel free to rewind this video and look at it as much as you want in order to try and improve your understanding. So we're going to build a model of the spread of a new disease. And this disease is spread through close contact with infected individuals. We know that the probability of someone catching the disease after coming into contact with an infected individual, which is known as the transmissibility, is 20%. And we know that the disease lasts on average for 10 days, although, as with all our modelling, we'll be incorporating some variability into that. So we're going to build a model of the spread of this disease within a population. So make sure you've got your Spider up and running, and you've pip installed MESA as well. So MESA models are typically comprised of three separate .py files, Python files. We've got one which is a file which contains the model itself. Now, you'll remember at the beginning of the SymPy session we talked about object-oriented programming. We didn't then go on to show you the object-oriented version of SymPy. Today you're going to be using MESA, and MESA is entirely object-oriented, so you're going to get a chance to see how this works. And essentially the file that you create for the model will contain classes, and remember that we said in object-oriented programming, classes are the kind of the blueprints for this is what a detainee looks like, and then we can create instances of detainees to use in our model. So in this case, we're going to create classes. One class which will contain the model. This will define the model itself. We will also have in this model file, we'll have one or more agent classes. We're only going to use one type of agent in this particular model, but you can easily imagine that you may want different types of agent in your model. So we've got we'll define a class for a model. We'll define a class for our agent, and we'll also have various functions to calculate results. And all that will be in this one .py file. We'll then have a separate file, which is the run file, and the run file will basically just run that model. And it'll either do that as a single run or a batch of runs, as we've shown you with SymPy, where you run the model lots of times to get sort of average results over multiple runs, acknowledging that variability will always incorporate randomness. Or we can launch a server that sends data to JavaScript so that it draws in a browser our model so we can watch it live. And that's actually the first way in which we'll build up our model. So we'll build our model, but then we'll create some really simple code that will then mean that you'll be able to watch in your internet browser your model play out. And you'll see the really nice visualization that MESA has. And then the third file is the server file, and the server file sets up the live model stuff that we've talked about above. Now, you won't need the server file if you were just doing batch runs. You'll only need it if you're launching a server so that you can watch the model run live. But initially, we're going to be doing that, so we're going to have these three different files. So let's start with the model file, because this is where we're going to put all the interesting stuff and build up our model. So start a new .py file. I want you to save that file and call it disease_model.py. You can call this anything you like, but for consistency of the training here as you're following along, this is the name I'll be using. So this becomes our model file. And as you know by now, first thing you do when you build anything in Python is we need to import the libraries that we're going to need to build up our model. So you see on the screen here, these are the libraries we're going to need to import. So just before you type that in, I'll just explain a little bit about what we're importing here. So you see the first ones, we say from MESA, import agent and model. So we want to import we don't want to import everything from MESA because MESA is huge. So we're going to import the concepts, the classes of agent and the classes of model, so that we can use those things and tell it when we define our agent class and our model class, this is a part of the agent and model classes defined in MESA. Also, from the time library in MESA, we're going to import something called random activation, the random activation class. That basically means that we can randomly order the order in which the agents in our model work and act. That will become more obvious as we sort of move on. From mesa.space, the space library of MESA, we're going to import something called multi-grid. That just basically means we're going to import a type of grid in which we can have more than one agent per cell. That's going to be important because if we're doing a disease progression model, as we are here, then it's going to be important to know when agents are in the same cell. You may have some agent-based simulations where only one agent can occupy any cell at any time. But for this purpose, we're actually interested in when people are close together. We're also going to import from the data collection library of MESA something called the data collector class. Don't worry too much about that. I'm going to talk about that a bit later later on in this course. So for now, just import the data collector. It's basically a way for us to monitor our data over time. And because we're going to be using some randomness, we're going to be using some of the random distributions, things like the exponential distribution. We're going to import the random library, as I suspect you're used to importing by now. So type in those import statements, pause the video while you do that, and then resume. Okay, so now you've got the imports. The first thing we want to do is create our agent class. We're only going to have one agent class in our model, and the type of agent we're going to create is a person. This is the kind of agent that's going to be important in our model, because we're interested in people spreading diseases. So people are going to be our agents. So in our agent class, we're going to have multiple functions that define the behaviors of our people agents. That will include a function to move the agent, because movement around the environment is going to be important. A function in which agents can infect other people. And a function which defines all of the things that the agent will do at each tick of the clock in the model. So at each time step in the model, we'll tell it to do all of these things. So it might be to move and then to infect people, etc. But the first function we need to define, and if you think back to our talk about object-oriented programming, you'll remember one of the key things we need to define is the constructor. This is all basically the functions that the function that defines all the things that we need Python to do when it sets up a new instance of our class. So in this case, we're creating a person class. So every time we get Python to create a person, we need it to set it up in this way. So in that double underscore init double underscore function, we're going to specify how that person agent should be initialized. And we're going to specify the transmissibility, that's the probability that it infects, the agent infects other people. The level of movement of the agent, i.e. the probability that it moves on any given time step. The average disease duration, and whether or not the agent's infected at the start of the model, according to a probability that we're going to specify. So all those things we're going to put into the agent constructor. So here is the constructor for the agent that we're going to write. So again, I'm going to talk you through this code first, and then pause the model after I've done that, so that you can type this out. So you'll see here, the first thing we do is define that this is a class. So we've defined class person agent, and the input to that is an agent. That's a MESA agent. Remember, at the start we imported the concept of the class agent from MESA. So we're using that here as an input. So what we're saying here to Python is I'm now going to define to you what a person agent is. So that every time you create one, these are the things that a person agent should have. And in our very first function in that class is our constructor, our double underscore init double underscore function. So as with any function, we declare that using def to define that function. So we're going to need to pass in certain things to the constructor. One of the things we're going to need to pass in is itself. And if you remember back to our object-oriented programming, we talked about how this is something we need to pass in when we can create a constructor in an object-oriented class. So we're passing in itself. We're going to need to pass it a unique ID to give to this agent. We'll need to pass it the model that it's going to exist in. The initial infection, which is going to determine the probability that this agent is infected at the start of the model. Transmissibility, which is the probability that at any time step the agent will infect others. The level of movement, which is the probability that at any time step this agent will move. and the mean length of the disease, which is the mean duration for which this agent, if they're infected, will continue to have the disease. And we're passing those things into the constructor because those are the things that we're going to want the user to specify and to change. So we don't want to hard code it, so we're going to pass that in and then get the constructor to set these things up. So you'll see the first line of code here, which is super.init unique ID and passing in the unique ID and model. Don't worry too much about that. That's basically just getting it to pass in set up the unique identifier and the model for this agent class. The rest of it, we're basically going to now want the Python to set up for each agent that it constructs, each person agent, to set these parameter values up according to the things we've passed in. So we say self because we're referring to itself. The constructor is within the person agent. So when it sets up a new agent, it needs to do these things to itself. So we say self.transmissibility, so its own level of transmissibility is equal to the transmissibility that we've passed into the constructor. So whatever we pass in, that's what we want the agent's transmissibility to be. Same with level of movement, same with mean length of disease. We're then going to use the initial infection, which remember is the probability that this agent is going to be infected at the start of the model. We're going to use this value that we've passed in, to now randomly determine whether this agent, as it's been created at the start, is infected at the start of the model. So we'll use the same sort of format that we've used before, where we use a random.uniform distribution, take a random number between 0 and 1, and see if that's less than this probability value for an initial infection. If it is, then we're going to set the infected parameter value of the agent to true. And this is a Boolean value we're going to use to determine whether the agent is infected or not. And we're also going to, because that agent's now infected, we need to calculate how long they're going to be infected. And remember, we said that that's going to be, we've got a mean length of disease, but we're going to assume in this case that the disease duration is exponentially distributed. So as we've done before, we're going to randomly sample from an exponential distribution using this mean. So remember, we need to specify lambda, which is the reciprocal of the mean, so 1 over the mean. So we're going to calculate it here by saying self.disease duration equals the random sample of how long it's going to, as a random sample from the exponential distribution using that mean length of disease. We're then going to round that because we can only deal in whole days, because we're dealing in days in our model, and then cast that as an integer because we need that as an integer value. If we randomly determine that this agent won't be infected at the start of the model, then we're just going to set the infected attribute of the person agent to false. So what I want you to do is now to pause this video and just write that code as you see it on the screen there. Okay, so the next thing we need to do is to write our movement function of our person agent. Remember, one of the key things that we're going to need our agents to do, as well as infect other people, is to move within the environment. Now, the movement function will determine how our agents will move around the grid of cells in our environment. So in this model, we're going to have it so that our agents will move to a random neighbouring cell. So they'll pick one of the, and we're going to include diagonals, which is known as a Moore neighbourhood. So we're going to include all 8 neighbours, all the 8 surrounding cells, and basically at each time step, the agent's going to pick one of those to randomly move to if it's determined that the agent's going to move. We're also going to have it so that more than one agent can be in any one cell. As we said, that's going to be important if we're going to be modelling infection. So the first thing we need to do is work out for each agent what the possible movement locations are based on the cells around the agent and then pick one at random. Then we're going to tell the model to move the agent to that cell. That's basically what the movement function is going to do. So here is the movement function. So again, I'm going to talk you through the code and then give you a chance to write that. So pause the video once we've done that. This is another function within our person agent class. So this will, in this case, this is going to be our second function after our constructor function. So we called this function move. Again, into this function we pass in itself. That's the input. The thing that we need for this function to run is just the agent itself. So we define the move function with an input of self. First thing we're going to do, as we said, we need to work out what are the possible cells that it could move to. So what we've done here is just to say, okay, let's store in a variable called possible steps the list of possible cells, and MESA allows us to do this really easily. So we can call within itself the model, because remember we passed in the model to this agent. So within itself, the model that we passed in, within that we can grab the grid that it exists in, and we can call a function called getNeighborhood within that grid library. And getNeighborhood will grab the neighbouring cells, and that's what we're going to need to know to determine which cells it can move to. And we've given three inputs to this function: the current position of the agent, which remember is itself. So the self.pos means my current position. More equals true means include the diagonals, so include all 8 surrounding cells. And include center equals false basically means don't include the center, because that's going to be the one where I'm currently at. That isn't a valid. If I'm going to move, I may not move, but if I do move and this function gets called, then I can't move to the same place I am now. I have to move to one of those neighbouring cells. Once we've determined which of the cells are valid movement locations, we're going to then select one of those cells to be our new position. And remember, we said that in this model, we're just going to get them to randomly pick one of those cells. In various different agent-based models, you may have logic, so you may have agents that are moving towards something or follow a certain pattern. But in this case, we're just going to keep it simple. We're just going to get them to randomly pick one of those 8 neighbouring cells. So the new position variable that we've got here, we just want that to store one of those 8 neighbouring cells chosen at random. So we can just use the random.choice function and as an input give it the possible steps. So in the possible steps we've stored using that MESA function, we've got it to grab the 8 neighbouring cells, and then we just say random.choice with that list of cells as the input to say, right, randomly pick one of those 8 cells now. Then the last thing we need to do in the move function is to then move the agent. So we've looked at what the 8 cells are, 8 neighbouring cells. We've then told it to pick one of those at random, and now we just need to tell the agent to move to that chosen cell. So the way we do that is by using this function. We say of myself and the model that I exist in, that has been passed in, and of the grid library, we're going to use the move agent function. And so the move agent function, again, is something that's set up in MESA, and it just takes 2 arguments. The first one is myself, that's the thing I need to move, myself, and where I'm going to move to. So in this case, new position, which is the thing that we've defined above by randomly choosing one of the 8 cells. So it's actually quite straightforward. We've just got 3 lines of code, essentially. Find out what the possible cells are that I can move to, pick one of those at random, and then move there. And MESA simplifies all this because it allows us to use these functions to say, in a single line of code, grab my neighbouring cells, and in a single line of code, move myself as an agent to that new position. So pause the video now and write out that new function within your person agent class after your constructor function. Okay, so hopefully you've now written that movement function. So remember we said that we also need, in addition to getting agents to move, we also need them to infect other people. So we're going to need to write an infection function. So infection here works as follows. If a person is infected and they're in the same location, the same cell as non-infected agents, then there's a probability that each of the non-infected individuals in that cell will be infected. And remember, that's the transmissibility that we set up right at the start. The transmissibility defines exactly that probability that for each of the non-infected agents that are sharing the same space, the same cell as an infected agent, that's the probability that they're going to get infected. So the infection function defines how this works. What we're going to need to do is basically to tell it to, first of all, get a list of all of the agents. If I'm infected, get a list of all of the agents in the current cell where I am now. If there's more than one agent in that cell, i.e. more than just me, then we're going to need to go through each of the other agents in that cell, check to see if they're infected or not, and if they're not already infected, then with random probability determined by the transmissibility, we're going to infect them. And then if we infect them, we're also going to need to randomly sample the disease duration for that newly infected agent, as we did in the constructor if we determined that this agent was going to be infected at the start of the model. So let's look at how this looks in code. So here's our infect function. Again, this is another function within the person agent class. This is a follow on from our move function. So in this function, again, the only parameter that's passed in is the self, the agent itself. The first thing we need to do, we said, is to grab a list of all of the agents that are in this cell. So I've got a variable here called cellmates. That's going to store a list of all of the agents in the cell. Again, MESA makes that easy for us because we can call this function here of the grid within the model called getCellListContents, and the only input we need to give that function is my current location as an agent. So self.pos, remember, gives my current location. So if I give that, then we can then get that function to say, okay, that will now return into the cellmates. That will return a list of all of the agents that are in this cell. So now we've got that. First thing we need to do is check if there are other agents here, i.e., is there more than one agent in cellmates? Or in other words, because this is a list, is the length of cellmates greater than 1? If it's not greater than 1, if it's just me here, then I can't infect anybody else. But if it is greater than 1, then we need to start determining if we're going to start infecting people. So we say for each agent that's in this cell, so I've called it inhabitant here, but you can call it whatever you like, for inhabitant in cellmates, so go through that list in cellmates, and for each of those elements in that list, which I've called inhabitant, if that inhabitant is infected, if the infected attribute of that agent is set to false, if they're not infected, so if that infected attribute is set to false, then we need to look at whether we're going to infect them. So if that is false, then we're going to then randomly determine, using our uniform distribution, we're going to pick a number between 0 and 1, check if that's less than the transmissibility, exactly the same as we did in the constructor, and then if that turns out to be true, in other words, we randomly sample that we are going to infect this inhabitant, then we're going to then set that inhabitant's, that agent's infected status to true, and then randomly sample their disease duration from the exponential distribution. So remember, the agent itself, the agent for whom the agent that's actually running this function, will also be one of those inhabitants in the list of cellmates, but they won't be able to infect themselves because they're already infected if they've got to this stage, and so they won't meet this condition of if inhabited dot infected strictly equal to false. So write out that code, pause the video, write out that code, and then resume once you've done that. So we've defined functions to move the agent. We've defined a function to infect other agents, and we've defined our constructor. The last function that we need to write at the moment is a step function, and basically within MESA, each agent has a step function. The step function defines the list of things that each agent needs to do at each time step in the model. And that's typically a combination of the functions that you've written elsewhere in the agent function. So if we think about what we want our agents to do in our model at each time step, there's a probability that at each time step our agents may move. They may infect others if they're already infected, and they might also recover if they're already infected, because we need to check whether their disease duration has now elapsed. So what we're going to do in this step function is to first check whether the agent's going to move. And remember, we had something called a level of movement, so that's going to determine the probability that the agent actually moves on this time step. Then, if the agent is infected, then we're going to call the infect function that we've just written to potentially infect others if there are others in that cell and they're not infected, and we randomly determine that they should be infected. And we're going to decrement the agent's disease duration, this agent's disease duration, by one time step, which we're representing as days in our particular model, but they can represent whatever you like. So check if you're going to move, check if you're going to infect other people, and then decrement my own disease duration if I'm infected by one time step. So here's what the step function looks like. Again, we're passing in itself as the input. First thing we need to do, determine if we're going to move. So remember, we've got level of movement as the variable that's storing the probability that an agent will move on any given time step. So we can use the uniform distribution to randomly sample a number between 0 and 1, check if it's less than that value. If it is less than that value, then in order to move, all we need to do is to say, call my move function, my self. So self, to refer to myself, call my move function, which we've already written. We've told it what to do if it needs to move, where it grabs a list of the 8 neighbouring cells and then chooses which one it goes to, etc. So it's only going to call that move function if it's randomly determined that it is going to move. So the higher the level of movement that we specify in our model, the more likely it is that an agent will move at each time step. Next thing we're going to do is to then check if we're going to infect people. We can only infect people if we ourselves are infected. So we can check our infected status of ourselves. If that's set to true, then we're going to call the infect function that we've just written. Remember, the infect function would then go through, look at how many agents are in this cell. Is it more than just me? If it is, check to see if each one is infected or not. And if they're not infected, then randomly determine whether they do get infected. All of that happens in the infect function. So we just call the infect function there. And then if I am infected, we also need to reduce my remaining disease duration by 1 day. So remember, we can use this handy little shortcut to say minus equals 1 to decrement that value by 1. And that will decrement the remaining disease duration by 1 day. And that disease duration, remember, was randomly sampled using an exponential distribution when the agent was infected. Now we've decremented that, we can check to see whether this agent is, for this agent, their disease has now run their course. So we can say, is my disease duration now less than or equal to 0? If it is, then we know the disease has run its course. So we just set the infected attribute of myself, as an agent, to false. So that defines everything that's going to happen at each time step for an agent. So I want you to write that into your code. Pause the video here. We're actually going to end this video here because we're going to start in the next video to talk about the model and defining the model class. So what I want you to do, once you've written this, just for the next 5 or 10 minutes, just go back over all of the things we've written in our person agent class. Make sure you understand what each thing is doing. Go back through all the functions, all the things that we declared in the constructor. Just make sure you've got a good grasp of what's actually happening what we're defining in each part of the agent, in the person agent class. Once you've done that, once you're happy, so spend 5-10 minutes doing that, and then move on to video 3.